Alright, the second exam had 3 questions that were sort of open-ended, work things out. So sequentially, I'll try to go through these fairly quick. I strongly encourage you to pause and do the calculation rather than just copy what I'm doing. Also, I gotta forgive my fingernails. I've been doing a lot of yard work lately and I can't get my nails clean, so it's kind of gross. Anyway, first one, we got this thing about calculating the density of helium at a very low pressure and a low temperature. A couple ways to start this. I tend to describe this as being kind of an easy way. That the first thing we should do is recognize what this is. So we're trying to calculate the density. So absolute first thing to do is write out density equals mass over volume. Then we have a couple of ways to do this problem. We could come up with an equation that's a general solution to the density of any gas at specific conditions, or we could do it what I might describe as the easy way, and that is to assign something. So we'll just say easy, and the two choices that might come up is we could say, well, let's just figure out the density of 1 liter of hydrogen and all this. Alternatively, you could say, let's do 1 mole of gas. I tend to think 1 liter is easy because it'll make this denominator a 1, so it sort of saves us a calculation. So again, the easy way is we're going to let V equals 1 liter. I suppose that should be a capital L. Yeah, I'll do that. L for liter. Alright, now what's important here is we need to calculate the number of moles. And from moles, we're going to go to mass. So again, we're going to use the ideal gas law to get moles. We're going to use the molar mass to get mass of the number of moles that we calculate from the ideal gas law. So starting with that, let volume equals 1. We've got the ideal gas law, PV equals nRT. We need to figure out how many moles we have. So we have N is going to equal PV over RT. Equals, well, let's see, they tell us that we got 50 torr. We might jump forward and say, oh, but I need this in atmospheres, so I know that 1 atmosphere is 760 torr. I'm going to squeeze things in, see if I can fit it on the page. And I have 1 liter. Okay, and that's going to be over RT. R is 0.0821 liters times atmospheres, moles times Kelvin, and a temperature of was it negative 60 Celsius, which would be 213 Kelvin. Units all cancel, my torr cancel, my atmospheres cancel, my liters cancel, my kelvins cancel, and I have 1 over moles, which is going to give me some number of moles. Punching that in a calculator, we got 50 divided by 760 divided by 0.0821 divided by 213. We get a really small number. Most important is that we preserve our sig figs. So I get 0.0376 moles. Alright, working backwards. To find the mass is equal to moles times the molar mass is going to equal the number of moles there. I'll just not rewrite that, but that's that 0.00376 moles. Helium is 4.00 grams per mole, which gives me a mass, let's get rid of that, gives me a mass of 0.0150 grams, which is shockingly small, but so be it. And then again, kind of working backwards on my page here, my density is mass over volume, so that's going to be 0.0150 grams of helium per 1 liter of gas equals 0.0150 grams per liter. Pardon the crowding there, but anyway, grams per liter is the units. There's my answer. I had more space when I did it on scratch paper. I would be a little nervous about that being so small, but recognize the density of a typical gas is about a gram per liter. We're talking about something that is, yeah, what's that, 50 out of 760, 75, it's like 6% of an atmosphere, 7% of an atmosphere, so that's a factor of 16 less, plus it's helium instead of air, so I'd expect that to be a pretty small number. So boom, we're good. Everything works there. All right, think that through. And again, the important thing in my view very much is recognize what's going on. We got the definition of density. We recognize that somehow we're going to find the mass part by using the ideal gas law. You know, that's our connection to physical conditions to number of moles, and number of moles is going to be proportional to the mass. I mentioned that we could do this more directly. I could recognize that my numerator here is going to be N times molar mass, this bit right here. And I could recognize that my volume is going to be, wherever I did that, well, just going from this, it's going to be nRT over P. And so I could have N times molar mass over nRT over P. I could rearrange that and get an equation that would solve for any set of conditions. Alright, so that's number 1, or number 5, I guess. Be comfortable with that, and pause if you need to, and we'll go on to the second one. Second one we kind of did a lab on. You know, this exam, and typically I see it, is students have an inkling of what to do about normalizing, but we're not paying enough attention to units. So recognize that these guys are all percentages by mass. So if I had 100 grams of compound, I'd have 23.7 grams of nitrogen. If I had 1 gram of compound, I'd have 0.237 grams of nitrogen. So it's just a ratio. But the 237 here, 23.7, is a proxy for mass, not moles. A formula needs moles. So I need to take these guys, which are masses, and I need to convert them to moles. So if I maybe set up a quick table here, and I say whatever my element is, what are we doing? We got nitrogen, we got carbon, and we've got hydrogen. And our percents from the problem are going to be 23.7. I got 60.95. And I've got 15.34. And so formally I should just probably say, hey, let's just say there's 100 grams, so I'm going to convert these guys into grams directly. Again, I could just rewrite that, but 23.7%, if I have 100 grams, I have 23.7 grams of nitrogen. All right, then the important thing is I need to turn this into moles. I have a gram to mole conversion, which means I am going to look specifically at nitrogen and say 1 mole of nitrogen is 14 grams of nitrogen. 1 mole of carbon is 12 grams of carbon, 12.01, and 15.3 grams of hydrogen. Well, I have that 1 mole of hydrogen is, and this is just H, not H2, is 1.008, I'll call it 1.01 grams of hydrogen. So effectively I'm going to divide this mass for each element by its atomic mass. I do that, and that will convert it to moles. Again, the grams cancel, and I'm left with moles, moles, moles. So doing that for nitrogen, if I have 23.7, I'm going to divide that by 14, I'm going to get 1.693. That might be excessive sig figs, depending on what that 14 is worth, but it's important that we keep as many sig figs as we can, and maybe even bend the rules a little and keep extra. All right, we do the same thing for the carbon, and I take my 60.95, divide that by 12, and I get 5.079. And for hydrogen, same thing, I divide by 1.01, I get 15.12. And recognize this is moles of nitrogen, this is moles of carbon, and this is moles of hydrogen. Alright, at this point I have a ratio. So if this had been 1 to 2 to 3, it'd be obvious. But when it's kind of strange numbers, I look at this and I see 1.6 something to 5. Okay, what's that? Is that 3 to 1 or 1 to 3? You know, I can kind of see that this 5 to 15 is a 3 to 1. But what I do is I normalize. I'll put a big N here for normalize. And all that means is I'm going to divide all three of these by the smallest one. So I'll divide this guy by 1.693, which is of course 1. I'll divide this guy by the same 1.693 because I want to preserve the ratio. I'll divide this guy by 1.693. And I do that, and if I take 5.079 divided by 1.693, I get almost exactly 3. If I take the 15.12 divided by 1.693, I get 8.97. So pretty darn close to 9, though I need to recognize that. That's about 9, and I see this 1 to 3 to 9. So when I look at the formula of this compound of nitrogen to carbon to hydrogen, I have a 1 to 3 to 9. Okay, so we can ignore the 1 when we write this out, so properly this would just be NC3H9. If I wanted to be creative, with a little bit of organic chemistry or Vesper structures, maybe I'd recognize this as something called triethylamine, though that part's unnecessary. So that would work pretty well for it. But the correct answer here is just NC3H9. And again, ignore that 1 there. That's not really relevant. All right. So to summarize this one, what's important is that we went from grams, from that percent to grams. But what's key for a formula is we need moles. And then this normalizing process is that we're just picking the smallest one, dividing all of them by that small number, and that forces us to reference everything to 1. And then we hope that we get a ratio that gives us all integers. If it doesn't, there's some logic to do. I talked a bit about that in class, but if we got to go there, I don't know what we do. We shoot from the hip, cross our fingers, away we go. All right, so again, make sure this is clear. I thought this problem went okay. People recognized the normalization part, but I think the place that there was a lot of stumbling was recognizing that moles is what's important, the number of atoms rather than the mass of the atoms. And that first step of converting from a percent to grams, or more importantly from grams to moles, got overlooked a lot of times. All right, and then the last one was a big, long bookkeeping problem. So where are we here? So we've got a couple of things going on. Most importantly, we have the reaction. And that reaction is going to be that I have ethane, C2H6, reacting with oxygen to give me CO2 plus H2O. Quick balancing, I see 2 carbons here, so I might be tempted to put a 2 there. I should have done that in red, but I will. 6 hydrogens here, put a 3 there, count up the oxygens, got 2 times 2 is 4, plus 3 is 7 oxygens. This is O2, so I might have to do a 7/2 here. I could solve the problem keeping this fraction, but that's a little bit messy, so usually what we do is we say, hey, let's just clear this by multiplying by 2. So this is a 7, this becomes a 2, this becomes a 4, this becomes a 6. Alright, at this point it's a limiting reagent problem. And, well, you know what? Let's just start off a little table. So at the start of this reaction, I have 3 grams of the ethane, and I have 5 grams of the oxygen, and I have neither of those. And now we're going to kind of jump down a little bit. Maybe we'll preserve this as a table going forward. But we're going to have a limiting reagent problem where we need to ask ourselves, do we have, which is the limiting reagent? Is it C2H6 or is it O2? So if it's C2H6, our roadmap is moles of C2H6. Grams of C2H6 to moles of C2H6 to moles of, let's pick CO2 to grams of CO2. For oxygen, it would be grams of oxygen to moles of oxygen to moles of CO2 to grams of CO2. Alright, so we have that. And then we just do the calculation or set the solution up exactly. So my solution here is going to be that I have 3 grams of ethane. If I calculate that out, 2 carbons is 24 plus 6 is 30, so about 30 grams of C2H6 is 1 mole. C2H6 from the balanced reaction, 2 C2H6s gives me 4 CO2s, so 4 moles of CO2 is 2 moles of C2H6, and 1 mole of CO2 is 44 grams of CO2. Doing the same thing for oxygen, I got 5 grams of oxygen. Oops, ran out of space there. 5 grams of oxygen. 1 mole of oxygen is 32 grams of oxygen. From the balanced reaction, 7 moles of oxygen gives me 4 moles of CO2. And 1 mole of CO2 is still 44 grams. Alright, canceling units, which we should always do, but I won't do it because I'm writing kind of clunky here. But doing the calculation, 3 grams divided by 30 times 4 divided by 2 times 44 appears to give me, what do we got there? 8.8 grams of CO2. Recognize that I only had 3 grams and 5 grams of stuff to start with, so I know that's not possible. The second one, when I do that calculation, I get 3.93 grams of CO2. So that's certainly my answer. Alright, so if I go back to my table here, I started with that. I'm going to end with, well, I've determined that O2 is limiting, so I'm going to have 0 of that. I've got 3.93 grams of CO2. So I'm going to do the same thing to figure out, or similar calculation, but I don't have to do the whole thing for figuring out my grams of O2 to grams of H2O. And again, I know O2 is limiting, so I just have to do a quick calculation of grams of O2 to moles of O2 to moles of CO2 to grams of CO2. And doing this specifically, I've got 5 grams of O2. I've got that 1 mole of O2 is 32 grams. I have that 7 moles of O2 gives me 6 moles of H2O, and H2O is 18 grams per mole. So when I do this, I calculate out that I get 2.41 grams of H2O. So going back up to my table, I have 2.41. And here's a little trick because I'm running out of time. I have 8 grams here. If I add those two up, I see that I have 6.34 grams between them. So if I started with 8 grams of stuff, I have 0 oxygen. 8 minus 6.34 gives me 1.66. So there's my 4 answers. 1.66 grams of oxygen. Sorry, I have ethane left over. 0 grams of oxygen, 3.93 CO2, 2.41 grams. I could calculate the amount of ethane that got used doing a similar calculation, and I'd get 1.34. All right, there we go. Hopefully that makes some sense. I think I'm out of time. See you tomorrow.